Welcome to join me to the final lecture on section 4.1, lattice vibrations on our course on solid state physics. So in this lecture, we will essentially generalize our approach to three-dimensional finite, mono and diatomic lattices. And we see that many of the scalar quantities now become vector quantities. And in addition, we will look into the first Brillouin zone and we will discover that this Brillouin zone now turns into a three-dimensional volume that resides in the reciprocal space of the lattice. And what we learn here is that this generalization is maybe not the easiest and it is abstract, but it's very important because it really helps us to understand then in the future, for example, what makes solids metallic or dielectric or semiconducting. So please bear with me and I will try to explain things in detail and go through the basic terminology. I will provide a few examples and hopefully you will grasp at least the main things. And at least you should be knowledgeable of the ways how we should proceed when we generalize from 1D case to the 3D case. So this is what we will be covering during this lecture. And before using this developed treatment that we have highlighted, outlined here, and we want to do in the next section is that we want to calculate the heat capacities of solids, or specifically the lattice contribution to the overall total heat capacity. And we will need to generalize our approach to three-dimensional solids. And this is arising from the fact that many cases, when we are dealing with real solids, we actually must take into account the fact that the lattices are 3D and not just 1D. And what we do here, this is conceptually quite straightforward, but it requires a little bit of abstraction skills and a little bit of three-dimensional abilities, so spatial abilities, so that you will be able to imagine in your minds three-dimensional volumes of strange shapes, and then imagine these quantities that we're dealing with here inside that space. And I would say that if you are patient and you take the time needed, this is really nice generalizations because it really provides us more profound understanding of solid state physics and also physics in general. So please, even though this seems complicated, try to bear with me. This is actually quite good, important, and it's not that bad once you get the grasp of it. But just give yourself enough time. So what will happen first of all to the number of phonons and phonon branches is that they get tripled. And why they get tripled is that now in 3D case, we may have one longitudinal phonon oscillation branch, and that's shown in the left-hand side of the figure, so that the atoms can oscillate along the direction in which the phonons are also propagating. And then we may have two transverse phonon oscillation directions and phonon oscillations that are shown on the right-hand side picture. So now, if the phonon is propagating along from left to right, then we may have two oscillations directions. So the phonon may be oscillating, for example, along the y direction or out of the plane of here of the slide. And what this means, well, depending of course on the basis of the lattice, if we have a monoatomic lattice, then the lattice supports three phononic branches. So three acoustic branches are being supported, one longitudinal and two transverse branches. And now if we have a diatomic case, so we in fact have two atoms or more in our basis of the lattice, we will start having more. So the optical branches also emerge. So in fact we have now 6 branches. And this is of course due to the fact that we have the optical branches residing now in our dispersion relation graph. So this is what happens. Please take time to appreciate and understand where these numbers come from. And now let's then outline what are the variables that become vectors, and my apologies for the term proper. I just mean that they become vectors and they are not scalars. So please don't mix up proper vector and improper vectors into our discussion here. So we are not distinguishing between vectors and pseudovectors here, although I myself do distinguish their difference. And I did not want to say real vectors here because it may not be necessary that some of the quantities are real valued. So that's why I came with the word proper here. Maybe true vectors might be a good term here, because I don't think true vector means anything specific, but proper vector at least does have its own meaning when we are discussing physics. So essentially, with that, we are distinguishing between vectors and pseudovectors. For example, the electric field, a vector quantity, and a magnetic field, be a pseudovector. So lattice vectors, AI. So the lattice constants, in other way of saying, they become vectors. Of course, since the lattice vectors become true vectors, then also the reciprocal lattice vectors become true vectors. And the integer m that we were using, that was associated with a given normal mode, a given energy of the lattice, that also becomes a set of integers. So essentially that becomes nx, or mx, my, mm, z. So this is, sorry about the typo here. So it would be more logical to actually have integer n here, since we have nx, ny, and nz here. So this is what happens. We start summing, instead of like over m or n, we start summing over many indices. And as the name suggests, the wave vector also becomes a true vector. So k also starts having these kx, ky, kz components, and that's the nature of it. So in terms of definition, the k is the amplitude of the k to pi over an times nx, ny, and z, assuming that we have a cubic lattice, so that the lattice constants ai are just all similar constants a. So in the more general case, we cannot take the lattice constant out, but we should leave it here because the lattice constant might depend on the direction. So depending on what kind of lattice we have, what kind of lattice vectors we are dealing with. So this is what happens. The wave vector truly becomes a wave vector. And of course, the wave vector is the quantity that tells us in which direction our mode, our excitation is propagating. And now things become a little bit muddy, perhaps. So the concept of the first Brillouin zone, and I guess that's pretty unclear concept. First of all, we should really generalize that. And in 1D case that we were plotting the 1D dispersion relations, we noticed that the k is in the range of minus pi over a to the pi over 2. And this is a Wigner side cell, just in 1D case, but it is the lattice point that we were dealing with is in the center of the Brillouin zone. So in fact, it was already a Wigner side cell. But now that we go into a three-dimensional description, this first Brillouin zone now is seen to be a more conventional Wigner side cell of the reciprocal lattice. So what I wanted to say to you is that the first Brillouin zone, it's always a Wigner side cell, but now it just turns into a three-dimensional Wigner side cell that we're dealing with. And the important thing here is to remember that the lattice point is in the center of the Wigner side cell. So if we are in a real space description, the lattice point, that's usually where we put the atom or the basis, many atoms somewhere nearby, and then we formulate the Wigner side cell or draw the Wigner side cell surrounding this lattice point. But now we are in a reciprocal space, so we have the reciprocal lattice point at the center of the first Brillouin zone. And this is, I guess, usually the location where some of the students give up and they start thinking that the solid state physics is not their cup of tea, so to speak. But please do not just give up yet. Just give this a little bit time. And in the end, this is not the main point in this course. Even if this doesn't click in your head right now, just give it a little bit of time. few weeks at least, or this course. And then maybe at the end of the course, you see what happens when we generalize to this 3D. Why these things become as they do. And let's now go through an example. So the simplest I can imagine is the FCC lattice, so face-centered cubic, sorry about the typo. And that's quite common with the known materials. For example, aluminum, Al, that's forming an FCC lattice, copper, another metal, silver, gold, and among my favorites, diamond also forms an FCC lattice, but now instead of a single carbon inside the lattice point, we actually have two carbons, and they form a basis of the lattice. Silicon, also from the group of diamond, is forming a diamond structure. Germanium, similarly, when we go below in the group. And sodium chloride, for example, as an example of a ionic solids. So diamond, silicon, germanium, they are covalent solids. Aluminum, copper, silver, gold, they are metallic. And sodium chloride, ionic solid. So FCC lattices. And this is, we will be now looking what kind of first Brillouin zone we have for an FCC lattice, and then what kind of dispersion relations we roughly have when we are looking at these kinds of solids. So the FCC lattice and the first Brillouin zone of it is a truncated octahedron, and that sounds awful. And I guess when you look at it at the first time, it really looks awful. So this is now the Wigner side cell that we have when we are drawing the Wigner side cell of a cubic FCC lattice. So we have the different reciprocal lattice vectors B1, B2, and B3. And we have the lattice point here, the reciprocal lattice point, and then we are drawing a Wigner side cell surrounding it. So this is the smallest possible volume that we can come up with, that we can then form the whole reciprocal space by just putting these side by side. And then we are completely describing the reciprocal space without leaving any voids and spaces. And the Wigner side cells do not overlap neither. So this is what happens. And then we have these different terms inside, but more on that later. What these gamma, K, and W, and these things are in the Brillouin zone. So, and this is our first Brillouin zone. So now instead of a 1D case of a line graph, we actually now have a volume, and the dispersion relation is somehow some kind of surface of wave vector values inside this volume. And whatever these wave vector values and the associated energies are, these are the quantities that completely describe the atomic lattice vibrations associated with the system, since we're dealing with atomic vibrations right now. And this is what we need in order to understand what kind of states we have in our system, what kind of atomic lattice vibrations we have, what kind of phonons. And the trouble, of course, here, that it's quite hard to visualize if you would want to draw a dispersion relation, so omega k, in this general three-dimensional case. So how to draw this kind of quantity, a 4D quantity in essence, into a piece of paper, a 2D paper, or even in a three-dimensional volume. So this is problematic. And I guess this is the reason why it's not that easy when we are generalizing our treatment to 3D case. So we could, for example, plot isosurfaces of the dispersion relation omega k. So isosurface is a surface that we get out of the dispersion relation where in that surface the omega values are constant. So iso meaning similar, constant, and surface that it's a surface plot. And this would be one possibility, but that's not very intuitive neither, and that's not very, very, very easily used to understand the basics. So usually instead, we just draw line graphs, and that's it. And this approach has been found more useful. But the price we have to pay, that when we now are not drawing even surfaces, but we are drawing line graphs, that we need to restrict to only certain directions and locations in our dispersion relation. So in our first Brillouin zone. And how we do that is that we essentially are describing our dispersion relation by just introducing a few points of high symmetry, so specific locations in our Brillouin zone. And then we are drawing lines, the line graphs that are associated with lines in the volume associated with these different points. So we start with the first one. This is the so-called gamma point. And this is our origo of the first Brillouin zone. So this is where we have the reciprocal lattice point of our reciprocal lattice. So K is 0 vector there in the gamma point. Another point X, and this is then the point where the Ky is 2 pi over A. And this location has been shown here. So it's this point. And this was the gamma point. And then we have these other points, and I will show you what are the values of those. And these are the kind of points that are of interest. And these will be used when we are drawing a line graphs to try to understand what happens for the dispersion relation inside the volume. So then another point, L point, and that's defined, that's in the K value of Kx, Ky, and Kz are equal to each other, and they are pi over A. So that's the location of the L point. W, and that's in the location where the Kx is pi over 2, Ky is 2 pi over A, and Kz equals 0. So W is here. And then we have U, and which is in the location of Kx equals pi over 2A, Ky equals 2 pi over A, and Kz equals pi over 2A. I'm hoping that I'm not doing any silly mistakes in these. But also on the other hand, like from the Wikipedia, you can find these critical points, so these points of high symmetry. And final K that we describe is the location of Kx equals 3 pi over 2A, Ky equals 3 pi over 2A, and Kz equals 0. So these are the different points that we have, and that's where we have these. So there, for example, K, it seems to be, at least the Kz seems to be 0 here. So I'm kind of hopeful that I did not do any mistake. So these are locations that are of interest. And what we will want to do is that instead of like, for example, drawing an isosurface, we will draw 1D graphs when we are, for example, going from the gamma point to, let's say, to the X point. And this is a single line, and that we can draw as we can plot it as a line graph. And then we could, for example, go from X to W, and then we could also draw that line as a dispersion relation, as a 1D dispersion relation, and then we would be able to plot and understand things. And luckily, we do have, usually we only need to look into these very specific locations in our 3D dispersion relation, so that this is many of the times adequate description of the dispersion relation. And please remember that we are now considering a face-centered cubic lattice. These critical points, and of course the shape of the Brillouin zone will be different when we are describing a different lattice. So then we will have a different set of points when we would move to a different types of a lattice. So that's the complication that we have. Lots of different terms, and if you do not understand what's the meaning of them, it probably seems next to impossible to understand what happens. And here I'm now plotting an example dispersion relation using these critical points. So points of high symmetry. And we can now plot the most important regions of the dispersion relation. And this is for aluminum. Please remember, aluminum, it forms a monatomic lattice. So we do not have optical branches. We only have the acoustic branches. And as we can see, all of the branches, they tend to the gamma point, to the origo. And the dispersion relation here, nearby the origo, the gamma point is linear. So this is what we see in here. And we have the different dispersion relations and the different acoustic branches in our dispersion relation. So for example, what we are now drawing in here in this dispersion relation is that we are first of all going from the gamma point from the origo, from the center of the Brillouin zone to the X point. And this part here tells me how does the dispersion relation look along that line. So we are going from the origo to the X here. And now we are going then from X to K. So in fact, what we are plotting here is actually the line, the dispersion relation when we are going from the X point to the K point. And then again from the K point, we are going next to the gamma point. And this is the dispersion relation, the graphs that show what happens here. And then finally, we go from the gamma to L value and plot that there. And this is what we are plotting here. So this is how a real dispersion relation looks like when we are looking at the real solid. So it looks very complicated, but when you know what these terms are, what these points are in the x-axis, and you roughly remember that it's actually some kind of lines that we are drawing inside the 3D volume, that maybe hopefully then things start clicking and you realize that maybe this is not that impossible to understand. And all of these are acoustic branches. And please, let's now take a step back and think what this means in terms of the physics. So this dispersion relation and these acoustic branches, these tell us what kind of lattice vibrations may take place in our aluminum. And if we want to then calculate the heat capacities, for example, we must know what kind of energy states the system supports, because we need to be putting energy into these states that the system have. So we need to integrate or sum over these all possible states. And then we can calculate what could be the mean energy. And then we could try to calculate how this mean energy changes when we are changing the temperature, because that's the definition of the heat capacity. So we calculate the derivative of mean energy of the system with respect to temperature. So that's why we must go into these kind of complications, that we really must consider the 3D case, and that's how we would really calculate things when we would need to calculate things properly. We don't do that in our course. We will use a simpler treatment, but at least you should appreciate that how things should be done properly and how the quantitative agreement could be extracted. Then we should really calculate things in a more complicated manner. But that's way beyond the scope of our introductory course. We do not really go into that kind of calculations. Let's go through another example and then I'm done with this lecture. So let's plot the dispersion relation for a diamond. And diamond, as I mentioned before, it forms an FCC lattice, but now a diatomic FCC lattice. So we actually have 2 carbon atoms inside each of our lattice points. And what happens now is that we start seeing emergence of optical branches, because we have a diatomic FCC lattice, and that is visible here, that there seems to be some of curves that do not go into the gamma point, so that they do not have zero energy when they are at the gamma point here. And that's better way of saying it. So because of course this is gamma point is here when we have zero energy. At the gamma point, they do not have zero energies, the optical branches. And this arises from the fact that we have 2 carbon atoms in each of the reciprocal lattice points. So high energy branches, these are the optical branches as mentioned. And the branches that go to the gamma point, these are the acoustic branches of the FCC lattice. So please see that when we have acoustic branches, they actually tend to gamma point like this, and the energies associated will be zeros. And then I will spoil you already, but in the upcoming Debye model, when we actually calculate the heat capacities, we only estimate the contribution of phonons when we are residing near this region, and we do not consider these other regions in the dispersion relations. That dramatically simplifies our math, but that also limits the validity of the model to somewhat low temperatures, because we can just neglect the possible contribution of these kind of higher energy states. And final thing, I should mention you that please note also the difference in the energy scale with respect to or compared to the aluminum case. So in aluminum, the acoustic branches, the highest value of an energy of an acoustic branch, it went to around 40 milli-electron volts. And now with the diamond, we're seeing that we are easily going above 70 milli-electron volts, even when we are dealing with the acoustic branches and then their highest values. So aluminum, the highest value of acoustic branch, we would be somewhere here in the y-axis for the case of a aluminum, but with diamond, we're actually going considerably higher energies. I recommend you think for a while and look into the equations, that what this means in terms of the differences between diamond and aluminum, that what could possibly be explaining this quite clear difference in the values of energies associated with phonons. This is quite interesting, and when you realize what is causing it, I think you have learned quite a bit of solid state physics in terms of phonons, and I think that's a good like example problem you should try to solve. So I will now start just outlining what we do next in the course by asking you questions that why on earth do we care at all of these 3D dispersion relations, that why do we care, and what possible use this generalization has. And I will provide you the hint, I've said it already, that what useful we can do with this, but I will just hint before we move onwards, before I stop, that please compare this model against the Einstein solid approach that we have discussed, for example, in our course on structure of matter. So please compare now this n-coupled oscillators in 3D volume. Consider this case with the far simpler Einstein solid approach where we're dealing with uncoupled oscillators, and kind of like think yourself what kind of possible changes this may have on the macroscopic properties of the solids we're dealing with. But this is the thing I wanted to say to you during this lecture. Please, I hope you enjoyed. And this was the final lecture we have on 4.1 regarding lattice vibrations. And in the next lecture, we will move onwards and we will start calculating heat capacities that are associated with these kind of lattice vibrations. So thank you for listening, and please stay tuned for the upcoming lectures. Thanks and bye-bye.